Welcome to our live streams on building AI agents and talking with the builders and makers in this space. And today I'm joined by Abi Aryan. Hi, Abi.
Hello, Rod. What's up?
Well, you were saying just now that this is the second time that we're speaking, and this is correct. And it's been a while since we last spoke. And I always see you on LinkedIn, always writing very interesting things, always discussing various sort of like topics. And let's start by that. So, why not you tell us who you are and what you're doing? Because even I, who follow you, do not even really know what you're up to right now.
It's complicated. That's the answer. And I don't blame you. Sometimes it's hard for me to wrap my head around it. So I'm the founder of an AI startup called Abide AI. And what we are doing is we are trying to solve the decision layer for AI agents. So AI agents right now are fantastic at knowledge retrieval, but the moment you leave them to be able to make decisions autonomously, they cannot explain their decisions correctly. And that's where a lot of inconsistencies and the performance starts degrading, which is it flows back into the system when you have multiple agents communicating with each other. So
Mhm.
that's the problem we're essentially trying to solve. And the way we are approaching this is we're using a neurosymbolic approach, which is combining large language models with causal inference. So that's the work side. Then the other is the book writing side, on which I've just finished up LLMOps book. It's out now. I'm in the process of writing GPU engineering book. I started writing early this year, so now that's gonna be finished around March of next year, and then the whole production takes time, which is around 3-4 months, and then it gets released. Other than that, I teach HPC, high performance computing, at a university here in Portugal, in Lisbon. And I also do research in distributed computing along with the university itself.
Wow. And just starting there, so here, LLM ops and GPU engineering, there are maybe like two very different topics, right? So, or are they converging towards one? So why two different books yeah, so one for like LLM ops, the other one for here, GPU engineering.
So the focus for LLM ops was more like, the entire pipeline end to end, which would mean you're thinking about evaluation, which would mean you're thinking about data pipelines and the model and everything else, infrastructure and everything around it. But a lot of principles in LLM ops are like very much dependent on the organization itself, which is a lot of figuring things out depends on the company's culture, which is these are my requirements, this is what my latency is supposed to be, this is the kind of applications that we're building essentially. So in the LLMOps book, there was a massive focus on this is where we are going slowly, and this is the kind of framework you need to have, which is if there's an LLMOps person on the team, this is everything that they need to know and everything that they should be optimizing for. When it comes to GPU engineering, now that whole part of what happens within your data pipeline, what happens with your guardrails, how do you manage the security, all of that is ignored. Now the book says, at least the GPU engineering book says, this is your model. Let's optimize this as much as possible on your GPUs. It's purely an engineering book. There's nothing to do with whether you can afford to do it, whether you have kernel engineer or compiler engineers on your team. I don't care. It's basically like that book for absolute nerds, or like, okay, I know how to deploy my models. Now I'm going to optimize them and whatever it takes to basically be able to do that.
Mm-hmm. So if we start with the part of like here LLM ops and we think about current hot topics, for example, here MCP and similar, there is an explosion of frameworks and tools and ways how to do that, not only for MCP, but in general. So how to build AI applications. And I'm wondering here, when you look at all of them, how do you like evaluate them, categorize them? How do you know here this is hype and this is actually something is valuable?
So as of now, which is talking about very much like November, December 2025, we have a lot of frameworks, which is we have LangChain, people are using Pydantic and LangGraph, we have NAN, there's Crew AI, a lot of them. And to be told, in total, there, like I did run the numbers, around 350 to 400 agentic frameworks on GitHub alone.
Wow.
But
400.
all of them right now are delivering less than 5% success, end to end task success lift. So right now, more and more companies are going towards writing their own workflows and discovering this is the kind of problem that we are trying to solve, and this is the kind of agentic pattern that we're going to need. So the things which are still consistently moving the needle are, one is explicit long-term memory with vector, and then the other thing is basically optimizing for runtime model selection. So everything else, which is whether you're doing React pattern or whether you're going the plan and solve, whether you're doing tree search, all of that plateaus after 8% gain. So essentially, the things people need to focus on right now is A, how are you dealing with the memory? B, how are you dealing with the routing? And rest of it is mostly theater. So
Hmm.
um, I would very much go in that advice, which is like if you are able to solve those problems, then most of the frameworks don't even get there. And those are the core problems that you need to be solving. And most of the companies can start doing it in house. They don't need existing frameworks for that.
Mm. Those are two fascinating points, especially if I think that. So here for the memory, the value of something like ChatGPT for me increased massively the point when it started having memory, and then I don't need to repeat all the context, but just I say, "Oh, remember that we spoke about X and Y," and then it already knows. But from a builder perspective, if I want to add memory to my product, how do I go about that? I imagine it's much more than just I just choose a vector database and somehow I create some embeddings. There must be here much more behind.
Yeah, I mean, the most popular approaches right now is just doing KV caching, which is optimizable. But even for KV caching, again, because KV caching isn't really like, it doesn't just add to your memory when you're loading it up, it adds to the memory every single time somebody actually ends up running the model. So keeping the model small and then doing KV caching on top of that one, that's the way to go about this.
Mhm, mhm. And this is something that you cover in your book in LLMOps, or if I want to learn more, where do I go?
So I've mentioned the concepts in very simple details in the LLMOps books, which is very no hype, implement this, and even in infrastructure as well, which is I've mentioned it, which is whether you want to go sharding or whether you want to do manage parallel pipelines or whether you want to do data parallelism, go to deep speed zero. So I've mentioned up all of the tools, but when it comes to do you want to learn how to implement those ones, right now that's very much like documentations itself. I've not like the LLMOps book is not this is your hands-on workshop for like I will show you how to run the exact code.
Mhm, mhm. And here, thinking about building products with memory, are there any like tips, tricks, or pointers? So, like for example, how long should be that memory? Also, I imagine must be some restrictions in terms of like context window, maybe also so when I keep my embeddings and so on, which models to use. So, in general, if you were to let's say guide us through doing some first version for like a memory for our agent or our just AI product, what would that be?
So the first thing I would do is to first figure out for whichever model that you're using, don't always go down to the memory is going to be the problem. A lot of times there can be three different things, especially like I don't know if most people are doing self-hosted or they're doing cloud computing, or where if they're using up the APIs. But your models can be memory bound. They can be compute bound as well, which is you're making a lot of computations from scratch over and over again, or they can be communication bound, especially like self-hosted solutions. If you have already figured out that your problem is memory bound, then that's where you can start implementing kernel fusion techniques itself.
Mhm, mhm, mhm.
And that's where basically if you're seeing the models, the new models essentially, or if you've looked into like the DeepSeek's models, that's how they are gaining in terms of memory, which is how they're able to run these large models, which is they've changed up the architecture. They're using MLA architecture instead of like the conventional deep architecture. And the second thing is they're using their own DEP fused kernels itself.
Mhm, mhm. Thinking about your other book, which is on so here GPU architecture and engineering. So here what are you seeing? So, for example, the topic of GPU scarcity, is it something that is part of your book in thinking teams do not have access to the top of line GPUs and therefore they need to be very mindful how they use their GPUs? Or is it more about, for example, how do I scale my applications for GPUs? Or so basically, what is it that we can learn in this book?
So here's how I think about the book, or the way I talk about it is, so right now, when it comes to building up the models, it's not about how big of a model can you build, but is it the most optimal way to build the model? Which is, if you cannot do it bare bones, then you can't really scale it, or otherwise you're wasting a lot of performance essentially. So when it comes to my book, that is almost like the PMPP book, but written for the AI generation, which is, this is how you think about distributed systems, but for AI.
And
So it goes very much from me explaining, how to be able to profile the workloads. Then this is how CPUs work. This is how the GPU architecture works. Now this is how you handle the memory. This is how you handle the compute. This is how you handle communication. These are the libraries. This is how CUDA works. This is how PyTorch VLLM works, and then eventually going into kernel engineering. So that's essentially the entire book.
yes, and I want to go now in that if I think about, for example, just like classic deep learning, working very close to the GPU, maybe like implementing something directly on CUDA, or if not with PyTorch, will be less standard. But if I think these days about so here AI applications, AI agents, what we're discussing now, so here with KV caching, memory, and so on, this is a little bit more like higher level abstracted, where for my memory, I look for some cloud vector database. For my models, I'll be using maybe like something from OpenAI and so on. So for someone who's building AI applications, where does the GPU come into place?
So think about it this way. I have a system architecture diagram if somebody is curious on my LinkedIn, which is what happens when you press run on a large language model call itself. So which are the components if you go down within like a PyTorch call? At which point do you get optimizations from CUDA? At which point do you get optimization from, let's say, like prefill itself? So those are the components which you need to think about. For AI engineers specifically, if they're thinking about inference scaling, then they need to think about CUDA, then they need to think about PyTorch and everything else. But if we're not thinking about just inference scaling, if we're really thinking about like the data pipelines as well, that's the GPU engineering or the CUDA book is not really for them.
Mm-hmm. You just mentioned CUDA. So who should be learning CUDA now in 2025? Is there a specific subset of experts, computer scientists who should be like working with CUDA, or everyone who's doing AI should like looking at CUDA? Who do you believe is like the user for CUDA in this year?
Uh, Probably around 1% of the engineer, again, not 99%. So 85% of the gains that you can have in large language model inferencing right now are already within high level frameworks. So within like deep speed. So they have been extracted away. If you are already using these libraries, you can gain 85% of those gains. Now, let's say you're working with Alibaba, or you're working with ByteDance, where you now want to go from 85% to squeezing that remaining 15%. That's where deep CUDA specialization really matters.
Mm-hmm.
So
And
companies like Grok, companies like DeepSeek, companies like Esht, that's where you are thinking about how can I be on the inference speed leaderboard, because they are now serving massive number of people, massive number of organizations. The compute demands are massive. So even a small gain on those numbers, that 15% is billions in dollars.
yes, Eh, however, the majority of so here developers they're not working for these organizations, right? So they are more, let's say, for like startups or maybe like large organizations who are not necessarily here technology companies. So let's think about, let's say, like a shampoo manufacturers, all right? And in that case, is it still relevant for them to use CUDA, or here you say, no, actually, just focus on the LLM ops aspect of building an application and then just use cloud models and that's it?
No, if you're not planning to build a company to sell to a hyperscaler, then you probably don't need CUDA, unless you're trying to plan to be a hyperscaler or set up your own data centers in the future. So you don't need it. So shampoo companies, please focus on the LLM ops.
And so then talking about here this LLM ops aspect is also here we have the aspect of so here inference optimization. So where we are, for example, running an existing model, let's say a llama model or a DeepSeek model and so on, and we might be running this maybe like locally on our own GPU or maybe with some let's say like neo cloud like Twitter AI or similar. And for that we have different frameworks, of course, right? Like there is here a VLLM and the like. Are there any type of like architectural decisions or like frameworks here for this type of like inference and so like inference ops, we can call it like that, that makes sense? And should we be thinking about that as well, or is it again something that is very specific for just a subset and you'll say no, actually for 99% of people, then just take OpenAI, whatever it is they're offering, and you'll be happy?
So right now, if you are using API-based models, then obviously you don't need to care that
Yeah.
much about the cost of the models itself because you're transferring the cost to the company and they're happy to eventually go bankrupt for you. But let's say if that's not the case, you are hosting your models in the cloud on your own end, or whether you're building an on-premise solution, then VLLM is where you ideally want to start serving your models, because there are two interesting implementations. One is they have already implemented continuous patching as well as page retention. So from there itself, you can get up to 300 to 400% throughput increase itself. So that's enough for most people. Now, if you want to like literally go long context, then you would be looking at implementing something like Redux attention or going towards SGLang instead. And now, if you have compiler engineers on your team and you're going towards like the hyperscaler territory, then TensorRT LLM, and working on FP8, basically working on the latency side of things. And also then there's the place where you're thinking about how do I rewrite my own kernels to be able to get those small gains essentially. But most of the companies, I think they will still benefit from VLLM style serving, and also from using the existing frameworks. So using something like Ray to look into their pipelines, that in itself alone can basically cut your latency from like 60% to up to like 15% on an
Yes.
average.
Eh, all of that sounds like a lot to master. So we are talking about here like GPUs, also here about like inference optimization, different frameworks, different technologies. And I'm thinking, if I'm, let's say, like a backend developer right now, I've been building like APIs and so on, and working even, let's say, with TypeScript, right? So I'm like a Next.js developer, and so let's say, hey, AI is this big thing that I can miss, but where do I get started? So if I'm not an expert in this space, what's maybe like my first touch point? What should I look into?
So the first touch point should be the LLMOps book, which is understanding the entire thing.
Mhm.
And once you've really settled down on, I just want to focus on inference scaling. I don't want to think about the guardrails, because once you dig down into that one deep hole, you can't do everything. That's
Agree.
just the same advice on this. And once you go over there, which is now I want to do inference scaling, then go into what happens when you're making inference calls. How much space on the memory itself every single call is taking? How does decoding happen? How does the encoding happen? Which calls am I making within my PyTorch system itself that is translating to this? So what's the input and output out of every single component? Now then you start tweaking those components, and then you start looking into, okay, so like let's say flash attention, this is how flash attention actually worked. But then you have to get really, really zeroed in. And the moment you start going towards that direction, you can't really go back. Sure, you can. The ideal thing is don't go back, because then you start getting as close as possible to being a compiler engineer eventually. So if the goal is, I want to build my own Lambda current Lambda setups, which is like, or I want to create my own growth kind of company, or I want to work in semiconductors, or these are the chips I want to make, or whether I want to create chips that are optimized for large language models in the future of AI models, irrespective of the changes in architecture. Because again, I don't think we're going smaller ever in the future. Maybe a little bit, but we will always stay in billions at this point. Maybe not in trillions, but at least in billions. So if that's the direction you want to go towards, which is I want to be do the wizardry that most people are never going to see, feel free to go dig deep into like the inference scaling and the GPU engineering side of things. But if you're thinking about, I want to be the most valuable person in the company who can save my company, or who can save these entire pipelines. I want to be able to communicate with different teams which are not communicating right now. So there's a lot of blame shifting happening, which is, oh, this data was not managed perfectly. These data pipelines were broken. The prompt engineer didn't do their work right. These prompts could have been optimized better. So right now there's a lot of people that are working within these organizations. There are people in red teaming. Oh, they missed that. If you want to be the person who becomes the chain between all of these people, and this person can provide immense value, because then this person basically sits right below like the person leading the entire tech or engineering for the company itself. So think of them as like a solution architect, essentially. If that's the where you want to go, which is focus on cost optimization, saving cost for the company, then stay on the LLM ops layer.
Mhm. Do you have there any advice? So, what makes most sense for most people in that? So, for example, I imagine that doing some CUDA compiling optimization might be super rewarding, super exciting, but there is here a learning curve, might take some time to get there. And maybe there are other disciplines or activities that might be like faster to get where you want in terms of like being able to market yourself as a professional, but being able to get a job and so on. So, I don't know here if you have some suggestions for here our audience in terms of what to focus on, where's maybe like demand on the market, maybe also where you see here in terms of, let's say, time investment and results that you can see that makes sense.
Yeah, so one of the things that I see people often doing wrong, wasting time, is they try to pick up a CUDA book and start learning how to do CUDA programming. But if you don't know what you're programming for, then it's useless. So instead of going towards that direction, one of the most sensible things you can do is instead focus a little bit more on understanding how the GPUs work. And what I mean by that is really think about um, the basic patterns. So the very similar way when we talk about agentic patterns, it's similar. So think about a how is a GPU created, which is what are the main components? So threads, warps, and all of that stuff. Once you understand the basic components within like the GPU architecture itself, then think about what are the two key execution models that I can think about. So the two execution models always going to be the same, which is the two key models. One will be the execution model, and the second is memory model. So as long as you understand those two models, how they work, you're good. That's your first step. Then think about what are the performance laws. There are four main performance laws with every single GPU, no matter which language, whether you're doing CUDA or whether you're using optimizing for AMD architectures, or whether you're looking at, I don't know, something else entirely, something in open source. So learn about occupancy, learn about how to do coalescing, learn about divergence, and how to do tiling and reuse. So just these four main performance laws. And at that point, you can start playing with the toy kernels itself, which is how to do vector addition, how to do tiled maximal operations, how to do warp predictions. Once you are able to master these, and there are already resources where you can actually do these things. So there's a website called leadgpu.com. They have these puzzles. Also Model, the company that was announced, I think last year, Jeremy sort of told about it. I think he's one of the advisors on the company. They have their own puzzles on these things as well, which is how do you build these toy kernels, and they have solved answers as well. And once you're able to do that, so you've learned the two key models, the execution model and the memory model. You've learned the mean for performance loss. Then you've played with the toy kernels. Now start mapping these to LLM kernels. And that's where you really start digging into CUDA programming itself. And that's where, instead of starting from CUDA first, go towards CUDA when you've at least done two of those things, which is learn the models, learn the performance laws. Then, as you're playing with the toy kernels, that's where you start learning your CUDA instead.
Mm-hmm. And for your LLM Ops book, you have a dedicated chapter on metrics. And I imagine also here now for the GPU engineering one, there must be also something dedicated about metrics. Here, I'm thinking, are there metrics that we should be paying attention to? Are there like here, let's say like a list of things that are important whenever we're either, for example, working here with GPUs or just like doing pure LLM ops? Because here you mentioned that the traditional metrics aren't enough. And first, why would you define as traditional metrics? And second, which are like the metrics that matter here for like the GPU segment aspect and then classic LLM ops, classic quote unquote?
So for the classic LLM ops, the metrics that really matter are more so around cost optimization. The second is around evaluation. And the third one is around your data pipelines. If you can master those three things, then you have a lot of things sorted. You don't really need to think about this is my model or this is how I'm doing a reasoning model or that model. That's not your job. That is an AI engineer's job or whoever is building up the models, because most companies, they're not at this point, most of the companies are not even fine tuning, right? They're using off the shelf large language models, and the goal is just to get these large language models to run, tie them up with your databases, and that's where you're winning. So those are the metrics really. When it comes to GPU engineering, the metrics are latency, the metrics are throughput, the metrics are compute, the metrics are memory. And yes, cost, but not cost in the sense of how much are we saving, but how efficiently was this done.
Mm-hmm. Talking about GPU engineering and working on GPUs, for that requires having a GPU, and there is so much on the market, right? Like so many models and so here families and so on. If I'm beginning and I want to start learning about working with GPUs, and maybe I want to buy something for myself, or maybe I want to rent it, what's like here like a starter GPU that I can start working with? So what would you suggest?
So one of the best investments right now is a 4090. Although you can start with a one smaller than that, but on a 4090 you can get about a good level of performance. You will be able to run not the massive models, but at least models up to like 27 billion parameters. So not more than that. But that's a really good place to start learning your optimization skills. The moment you start going, and then probably the next one would be if you're planning to make investment in those ways, because I have access to an A6000, but the 6000 Blackwell series is a good one. I would Too many people I see jumping directly to H100s and A100s. I would say no. If you don't cannot afford a Blackwell, okay, fine, no problem. Start with the 4090, then go to an A6000. With two or three A6000, you can get really good performance itself.
Mm-hmm.
Like at an organization level, not even at a personal level.
Yes, and all of them are like Nvidia products, but we're seeing also already for some time an explosion in the market on other options. So like there are all these so Google TPUs. Also, AMD has its own offering. Also, for example, now Apple they also have this shared so here memory, and one can also do like AI workloads in them and so on. And then also thinking about on the programming side, CUDA, there is alternatives like a Mojo, so for working here with GPUs on a higher level. And with that, I'm thinking, does it still make sense to focus on this like very NVIDIA centric stack in terms of getting an NVIDIA GPU, learning CUDA, which is basically only for like here NVIDIA products? Or should we be also looking in, for example, here like Mojo and other offerings in the market like TPUs?
So I think maybe one thing I could mention here before I go into TPUs is TPUs are fantastic, especially when you're running checks. But, and yes, I know this will create like a debate on PyTorch versus JAX, which has been long going on, and I see that debate happening every single day. But if you're running PyTorch 2.5 and Torch Compile and Dymer, which is these three in a combination, so this ends up beating JAX on a single node for 95% of the workloads. So switching to JAX or TPUs only if you need XLA. So that's the one thing where you really go deep on like a TPU level. The second thing is when you have a very massive scale on which you want to basically shard your models or your pipelines, which is, let's say, if you have more than 2K GPUs, that's where it makes perfect sense to now go that level. When it comes to your question about should we focus so much on CUDA, which is NVIDIA centric stack, instead of using, let's say, uh, ROCm, which is like the AMD stack instead. That's the reason I said first focus on like the key models, the execution model and the memory model, then learn about occupancy. Those things, which is those two parts, stay the same irrespective which kind of model it is. Then once you start playing with the toy kernels, it's a little bit easier to start with CUDA, and for the obvious reason, because there are plenty of resources out there, plenty of people if you get stuck to help you debug. So it's just the easiness of getting into things. But once you're able to work it in, like, let's say, one stack, then going on to AMD and learning how to do that on like the AMD stack is super easy. So you're not anytime locked into like that one ecosystem. And right now, there's Stanford's lab that is working on uh, getting the AMD systems up to par. I think also Hugging Face sort of launched their own work in this space, which is this is how you can start optimizing the Roku kernels on Earthstack. So they are trying to go very much in that direction as well. So I think the community is sort of rising up, but don't jump into the stacks. The stacks are always replaceable. There's a very strong chance the moment you see little bit of progress happening with the AMD itself, there will be three more competitors who will start coming in, because right now, till this point, NVIDIA was the biggest monopoly. But we'll see more Chinese companies and their own stacks coming up as well. So as long as you're tied to one stack and don't understand the fundamentals, you'll never be able to transfer your knowledge from one stack to another.
And you mentioned this debate between JAX and PyTorch, and it's been a while since I was like in that space, but I remember. So it was something where PyTorch and TensorFlow, they'll be here for like production, but then TensorFlow was more like legacy. PyTorch was taking it over. And then if I look at who was working with JAX, will be like very academic, and also those who really want to like create so tailor-made components just to prove an idea, but it will be not something that it will be used by actual, let's say like AI app developers, those who want something in production. And so it's been already a while. It's been like easily 5 years since that. What has changed since then? Where are people using JAX, and do you advise using JAX?
Unless you already have dependencies on Google TPUs, maybe not. I would still say stay with PyTorch, because a lot of frameworks are still developing around PyTorch essentially. And very recently, Anyscale also donated their Ray framework to PyTorch Foundation as well, which is it's going to develop internally as a part of that. Red Hat AI, again, they are working on VLLM architecture, and they're working very closely with PyTorch as well. So I'm seeing more and more companies converging towards PyTorch and building abstractions on top of PyTorch itself instead of on JAX.
PyTorch is also something that I find it as a drop-in replacement for something like NumPy and so on. So where's currently your like standing on the PyTorch? So should we all learn PyTorch? Is it like something that you say, hey, it is like staple tool, or do you see it really only if you want to go like deep in the weeds, then you should be working with PyTorch, otherwise just take something higher level?
If you're simply deploying up the models, then again, very much to what I said, which is if you're using API-based models, then you don't need to care. If you have self-hosted, or if you're self-hosted, whether on-premise or whether on cloud, then knowing how torch.compile works is enough. And then if you're going into weeds, then start looking into how the decoder works within the PyTorch, how all of that happens. But most of the people don't need to go into that direction unless that's the goal. Which is not like all of the AI engineers, maybe just one who's crazy enough to be like, I just want to be a nerd. I'm going to go become a compiler engineer eventually.
And so talking also about that, so here we're discussing about generative AI workflows, LLM apps, and so building like the next Grok. But do you have any overview on what's happening with these more classic workflows in data science, machine learning, where until very recently was, okay, I need to create a classifier, and I need to create like a regression model, and then I'll be programming this like on PyTorch, right? And then I want to optimize it. I'll be using here maybe like some GPU optimization and so on. What here are people doing? Do you have here an overview on maybe like modern approaches or current trends that are happening in these more like classic workflows in data science and machine learning?
So most of the companies that I've been talking to in that space, they are building up dashboards to be able to automate stuff. So right now, I'm not seeing many Gen AI workloads pay the bills at companies, and that's honest. The things that are still paying the bills are very much still classifiers and all of that stuff. The places where at least these are AI implementations have been successful is them being used as classifiers still. So for example, like let's say you're looking at KYC for people, which is these are the photos. And instead of having a person look at the photos to very quickly identify where the text seems to be photoshopped or something like that, that's where I'm seeing a lot of people use it. So for like very obvious work. The second thing is on like, let's say a company had a lot of Jira requests, let's say. Now classifying those Jira requests within different teams itself. So for this is for the sales, should go to the solutions team, this should go to the marketing team, and this is for something else. Those classifications are where I've seen Gen AI implementations being pretty successful. And the main reason people are using these ones is especially when it comes to replying to emails. So within companies, you don't have one person doing emails within your customer care team. You have multiple people within your customer assistant team. Every person has their own personality. Every person has their own unique way of replying to things, and depending on the mode, we don't write the same kind of language at all times. So what they're looking for is basically maintaining that consistency across the entire organization. Large language models allow people to maintain that consistency, at least on the surface, which is you give a prompt, this is the kind of language I want to use, it just does the same language. It doesn't go too far away from that language, essentially.
Um, if I reflect back also, one discipline that also connects to all this part of like GPU optimization and also like doing LLMOps is like model fine tuning. And I remember like about 1-2 years ago, people were saying, yes, like everyone will be doing model fine tuning, and then we'll be like here putting our own data inside and have like our own custom made models. But I must say, this year I hear definitely significantly less around some model fine tuning. And maybe it's my own bubble that I just not exposed to that anymore, and maybe it's happening a lot, but maybe not. What do you say here is going on? Are people fine tuning models, or is it something where maybe we had like some hopes and then that didn't materialize?
No, I don't see most people fine tuning their own models right now. Companies are still where. Because I talk to a lot of agentic companies right now as a part of my company, because we're trying to figure out the decision layer. So companies are very much at the level where they're trying to implement agentic systems. Where the big problems they're trying to figure out is how to make these workflows work. So the focus isn't really on fine tuning this to work this, but more so on how do we fix tool calling properly? How do we make sure that these are reliable at all points in time? How do we make sure that the costs stay optimized at all points in time? How do we have human in the loop eval pipelines? So thinking about latency, cost, and accuracy metrics, that's where most companies are right now, especially like as we are getting that reality check that people don't have infinite money within the companies. The only implementations when it comes to like the technical implementations itself that I'm seeing is the transfer from instead of fine tuning, now we're thinking about instead of calculating the inferences every single time from scratch, how do we cache these better? And yes, we were doing most of this stuff in feature engineering as well, which is we had feature stores that we were saving a lot of stuff in to cache them for later. So right now, the new one on the block, or not the new one, there's a lot of work around cache that came out particularly this year, which is more efficient. But the implementations I'm seeing more commonly are around KV cache. Are people trying to figure out how to do continuous batching? Are people trying to figure out how to do page retentions? So that's probably on the companies that have already gotten the systems right and now are trying to look for optimization. So the companies that were doing fine tuning, now they're doing KV caching, continuous batching, and page retention instead.
Mhm. Part of what you're saying now is that so here companies are looking into deploying agents. I'd say if so model fine tuning is not something that became popular this year. What it really became popular this year was doing agents and agent engineering.
Yeah.
And so here in your book, I wonder if you're covering here agents and in general. So is agent engineering a unique discipline? Is it something that it has its own things to learn, or will you say, hey, LLMOps covers anything about agents and that's it? There's maybe like something to know more, but 90% is what you need to know is in LLMOps. Or are you saying no, actually agent deployment is such another different thing in terms of what you need to think about that this cannot be dealt with the knowledge is covered on LLMOps or in your GPU engineering book?
So in the GPU engineering book, I'm not covering agents because that's on the application side, which is how do we apply, how do we work out the workflows. That's not even the focus. The focus is really like inference speed down to the components. But one of the things I've said in the LLMOps book itself, which is when it comes to the application, think about large language models as software 3.0. Any applications that are building on top of that, whether that's a RAG application, whether that's an agentic application, is software 3.0. And the moment you start thinking of it in software, then the whole part of every single best practice that was relevant earlier, which is most of the people were, at least in 2023-24, most of the people were thinking about large language models in like a very monolithic way. So going more towards microservices-based architecture. So the whole transition that happened in cloud software development thing in 2012, now that's the same thing which we need to replicate for like these agents to work, which is instead of thinking about large language models as these monolithic architecture, now start thinking of them as modules and microservices within a larger system. So the same principles do apply, which is LLMOps book is not really about this applies to large language models, but anything that is built on top of large language models, essentially.
Mhm, mhm, mhm. Um,
Like
you
it's a
are
frameworks book, very very similar to how DevOps used to work. So DevOps is not something which would be relevant for like just the finance applications or just the retail applications. As long as you were doing software, DevOps mattered.
so therefore that means that anyone working with AI should be doing LLMOps or learning about LLMOps, just like
Ab-
DevOps is like this is foundational layer that one needs to know.
Absolutely.
Mhm. And thinking as well as about so here small models. So we're talking about a GPU optimization and deploying apps at scale and so on. But what about on the other side, on these small models that we can run with Olama on our own laptops and so? Where do you see them here in place, and do you use them? Do you recommend them? Are they more than just toys and like little things. For example, I use them when I'm teaching things. I like to work with So Hero Llama because it's such a basic thing for everyone to run and doesn't require any cost. Any student can use them. But at the
Mhm.
same time, of course, it's very easy to see the limitations in terms of like the context window, what the capability and so on. So where would you here place small models in all this landscape that we're exploring in LM ops, GPU engineering, and so on and so forth?
So most of the models that you're seeing on Olama as well as like let's say LM Studio are highly quantized models to
Mm,
be able to run them on these laptops essentially. And the best thing about that is yes, we can now run them anywhere and very quickly build things up with them, show them in demos. But most of the applications still stay very much up to demos. The moment you start hooking them up with VLLM, let's say, to be able to serve these models in production, then you start hitting up a lot of problems essentially.
mhm, mhm, mhm. Um, and so thinking about here like the future and so on, right? Like we were describing that basically we're almost like in December. So 2026 and so on is like approaching. So maybe you have here some predictions or things that you're seeing that are nascent. This year was the agent, the year of the agents. What's await us for 2026?
One of the things which is I would probably say we would move away from quantization. Everybody was going towards FP16, FP8, FP4. We've gone towards all of that, and most of the people were thinking, quantization was essentially solved at 4-bit. Now, I think what we would see is more overall. People thinking more so around how do we do dynamic per token scaling. So that will be one of the big focus. The second thing will be maintaining the accuracy loss even at 70 billion architecture, which because that's a massive thing. So for example, when and the third problem would be the context management itself.
Mm,
So very quick example I can give you, even with the big company. So if you're using Cursor, there are a lot of times you will end up with the model being in a loop, which is you have a question, it answered it. Now, even if you ask another question, it doesn't consider your question and it keeps repeating, parroting the same answer and over again. Same happens with the Gemini models, which is if you give it one image to, like, let's say, read the text from this Instagram post, and then it will answer those things perfectly. By the second or third conversation within that chat itself, within that small context window, it completely goes off and starts hallucinating. So that will be the big problem which I see most people trying to solve, which is the accuracy loss, then going towards a little bit more around per token scaling.
mhm, mhm. And that's on this hardware level, but what about the application layer, the agent layer, and so on? So when we go up in the stack, which things do you expect next year happening?
So one of the things I talk about a lot with the companies is they've implemented their own agentic systems, but
Mm,
right now they want to figure out what's going on, which is how can they provide better prompts, or if the output was a certain way, why was that output that way? Can they debug those systems? So more work around observability within the existing agentic applications, which comes down to the why this response came out like this, and not going more towards the model itself, but just being able to explain these are the sources
mm.
because of which this decision was impacted, and being able to quote the exact references and citations essentially as
Yes.
accurately as possible.
Mhm, mhm. Mm, I like to spend some minutes so understanding more about what's about AIs. If I'm now like I'm listening and saying, "Wow, here Abby, she's such an expert," and somehow I want to collaborate or do something together with her. And why? How can I do something together? And then also, where does here about AI comes into place in all this?
So we have built in an internal observability tool itself, which we will open source very quickly for just this particular application itself, which is if you already have existing agentic systems and you want to figure out what's going on within those agentic pipelines, how the runs are happening, how many calls are being made, how different agents within your pipelines are being called, why are they making those certain decisions, then that's where that would come in. But most of our actual work is on the research side, which is building up the reasoning model and then doing a lot of work around taking existing reinforcement learning environments. So OpenAI Gym, using mini-grid, and now adapting them, which is introducing curriculum learning to them to now optimize these neurosymbolic models essentially. So we are trying to now go towards the direction, not go towards, which is, it was the goal essentially, which is win the AGI 3 competition. So win those benchmarks, that's the goal. Right now, most of the large language models, they are awful at object manipulation. They cannot tell when an object has been manipulated. They cannot understand it. So those are, again, the problems that we are trying to solve.
So Abad AI is an open source agent
A
observability
deep tech
platform, or
company. It's a deep tech company where our focus is on research and on research on reasoning, essentially, which is how do we make models be able to reason better.
Mhm,
Um,
mhm.
that's the main company. And as a part of that, yes, we are releasing certain tools which we built in house, and all of that will be open source.
Wow. As the last thing I'll cover is how do you find time for all this, Abby? So I'm hearing like the books, all the activities that you're doing. So here about the AI, all of these are yeah, very time consuming, so very intellectual activities that require a lot of like time for that. So they share with us some productivity tools. How can we do as much as Abby can do?
I don't know if I have productivity tools, but I think I can give people a mindset shift, which has been very helpful for me. Um, a is don't focus too much on the goal, which is and how to get there, which is think about this is the problem that I'm sort of interested in, but don't get too worked up about this is the exact direction I want to go in, or this is how this should be executed in my life. Like most of the things that have happened to me are not exactly the things I planned. In fact, they were exactly the things I was trying to avoid. I was one of those people who was trying to go into finance and be the VP at Goldman Sachs. It just didn't happen for me because I turned out I did not like the finance people as much hanging out with them. I ended up falling in love with engineers, and that was my comfort zone. And I've stayed in the comfort zone. So that is one thing, which is don't get too worked up about this is how I'm going to succeed in life. You don't know how you're going to succeed in life. There's no strategy to reverse engineer your goals. If it's meant to be, it will be. When it comes to time management, I think more than the time. So, for example, you don't see me posting too much on social media. I only make, even now, I still make 1 or 2 posts a week. I only post a newsletter once a month. So think about quality instead of quantity. Quantity is important, but first nail the quality of your work, which is if you're working at any company or if you're working on any one project, think about how can I make sure that this project is really substantial. Digging deep into things will give you much more understanding and exposure than working on 100 million things. I didn't start out doing these all things in parallel from the get-go. I was working as an ML engineer for like last 10 years. So I have really worked on that. I've been reading books since I was a baby. I've wanted to write books since I was 3 years old, and I ended up writing a book at 30 years of age. So it's a very, very long journey where you have to let things simmer up. And the moment you're ready, the moment it comes and you feel confident, then jump into that thing.
Mhm, mhm. Yes, I see with you that so on one side, maybe like focus on little things and not try to do too much on some, but still is fascinating how you can achieve so many things and also all the journey. So what we're seeing here, all the knowledge that you have on GPU engineering, GPU performance, as well as higher layers on. So here the AI stack. And I'm very curious to see when your tools will be open source, and I love to look at them once they're live. And so for anyone who wants to follow on all that, which are like the platforms where they can find you? How can they like engage if they have like questions about so GPU optimization? If they want to know more about AI, what are here the platforms to look for you?
So for Abide AI, which is if you're interested in reasoning, we already have two papers on archive, and we have long blog posts as well, which are very research focused. So if you go on the website itself, go under blogs, you'll be able to find the research work that we've done and how to be able to contribute as well, which is on the paper itself. It's necessitated to be able to mention the future direction or the limitations of this work, and you naturally know those are the limitations that we will be working on in the next paper. So that's a fantastic way to be able to work together or start moving in the same direction. When it comes to GP engineering, again, the blog, and I'm more active on LinkedIn these days, and I think I'm going to be more active on LinkedIn itself. So those are two good places to sort of follow me. I'm not going to be creating content every single day. It will happen twice a week. The blog post will come out once or twice a month. That's fine. But as long as you even consume that, I say to all the time to people who say, "Oh, Abby, I've read your book on LLMOps," and I'm like, "No, you haven't. Nobody reads books end to end. Stop lying to me. Tell me what you need." So don't try to consume too much content. Don't, and I'm not saying it because I am trying to give bad advice, but far too many people go into this analysis paralysis where they collect far too many things and don't really actually take time to absorb and process and analyze all that information. So really pick up your resources, pick up, let's say, three people that you like, and I can probably name those three people for you. So, for example, Paul is a really nice guy to follow on social media. Paul Lutson, the author of LLM Engineering. Maria, I don't know how to pronounce her last name, but she is one of the Databricks MVP as well. I think most people know about her. So she does post a lot of material around uh, MLOps as well. So she's one of the really interesting people to follow. Then Eric Ridock. Eric also posts a really interesting stuff on MLOps, but more so focused on who are the vendors essentially. So all the vendor side of the things he talks about. And then Joe Reese for data engineering stuff. So if you just focus on the few key people and then consume what they're putting out religiously, then you're naturally elevating with them, because these people aren't perfect. They're learning every single day and they're sharing their learning with them. So you have somebody sort of guiding you, and then you're sort of growing with them instead of getting distracted with 500,000 people.
That's a great advice. And yes, so if you're saying three persons to focus on, then one of them should be here, Abby, that everyone should have on their list, plus two other from the ones that you mentioned. And that's like a really good way to wrap things up so for today, Abby. Thank you so much for spending here the time. And for everyone else, every week we're doing here our different live streams where we talk with experts such as Abby here on how to build AI applications, AI agents, and everything around that. So for example, now with all this fascinating world around GPU optimization, it is great that you were here today, Abby, and we'll look forward to see where you'll be publishing both on here deep research publications in archive and so on, as well as, of course, more social media related content on LinkedIn. So I'll be looking forward to that. And until next time, Abby, thank you so much.
Thank you so much, Rod.